So hello students, welcome to Analog Electronic Circuits Revision Lecture number 1. So we are going to revise the Clipper circuits which we have studied. We have studied around 4 of them in the class. So clippers are the networks that employ the diode to clip away a portion of the input signal without distorting the remaining part of the signal. So simply put, clipper circuits do this. So this is my sinusoidal signal. This is my input and output is marked in this color, and it either clips the positive part, so it's called as a positive clipper, or it clips the negative part, it's called as a negative clipper, or it clips both the positive and the negative part of an input signal, which is called as a combinational or a two-level clipper, right? So what are the clipper types? The clipper types are categorized as I've just said. A positive clipper for the positive portion of the output waveform getting clipped, negative clipper for the negative portion of the output waveform, series clipper in which the diode is connected in series with the output, shunt clipper, the diode is connected in parallel with the output, combinational or a two-level clipper where both positive and a negative portion of the output waveforms are getting clipped. And out of all this, we have a bias clipper wherein there is a provision to adjust the clipping level. That means a DC bias voltage is in series with the diode connected. So this will cover all the types of variations. All right. And in the clipper circuits, the main clipping element is the diode. Okay. So let's go to clipper number 1. So this is my circuit which is shown to us. All right. So we have a voltage applied Vx. All right. And the current flowing through the circuit is Ix. I have my resistor R1 basically to limit the current through the diode. My voltage across the diode is VD1. Okay. And I need to plot the input output waveform with respect to time. And I need to plot the voltage transfer characteristics. That is the VTC curve. Let me add it over here. This is my VTC curve. All right. And we should note that the value of the R1, if we are designing the clipper circuits, should be selected higher than the on-state resistance of the diode. Now, on-state resistance of the diode, the resistance is somewhere around 1 to 10 ohms. Okay. So value of the R1 should be greater than this value. And we are assuming a constant voltage model. Constant voltage model for the diode means what? This, this picture. All right. So what does that mean? It means that diode will be on if my if my applied voltage VD1 is greater than VD on. So here diode D1 is on. And if it is less than that, the diode D1 is off. Okay. And how much is this VD on? Anyone can tell me? You remember? What's the value of the VD1?
Point 0.7 volt.
Yes, it's 0.7 volts. So this is my constant voltage model for the diode D1. All right. Now, if I apply the KVL around this loop, I'll get Vx is equal to Ix R1 plus V out. Okay. So Vx is equal to Ix R1 plus Vd1 or V out, because Vd1 and V out are here almost same because they are in parallel. All right. And what did we say about the applied voltage? If Vx is less than Vd on, then my diode will be off. If Vx is greater than Vd on, then the diode is D1 is on. If it is less than, D1 is off. Okay. And when the diode is on, it is replaced with a short circuit and a battery of Vd on. And when a diode is off, it is replaced with a open circuit. All right. So these are the things which you should keep in mind before solving a clipper circuit. So can we proceed ahead with this? Okay. So let's consider the first case. Vx is less than Vd on. So this Vd on is the clipping level in our case. So that is around 0.7. First, let us solve generalize and then at the end we'll put the numbers. So for Vx less than Vd on, diode D1 is off. So whenever the diode D1 is off, it is replaced with open circuit. So here it is, open circuit. So here the circuit reduces to this network. So since it is open circuit, current Ix will be 0. So what can we say over here? V out is equal to the input Vx. So that here we can say that the output voltage follows input changes. Okay, whatever is the shape of the input, the same output will follow. So this is the case for Vx less than Vd on. Now for another case, Vx greater than Vd on, the diode D1 is on. So there was a diode connected over here. It is replaced with a battery of Vd on and a short circuit. All right. Now in this case, since the diode D1 is on, what will be my output voltage over here? The output voltage will be same as this Vd on because they are in parallel. Okay, and this will be Vd on. And later on, we can substitute that Vd on is equal to zero point 0.7. That is for later. All right. But initially, this is the picture. So for any voltages Vx less than Vd on, output is equal to input. That is output follows the input. And for any input voltages greater than Vd on, the diode 1 is on. So output is equal to Vd on. All right. Everyone understood this? Yeah. So let's plot the VTC curve. So over here, Vx less than Vd on. Okay. So let's plot this picture. So this is my VTC curve. On the x-axis, I'll plot the input. So this is my input Vx. So what are the conditions? For Vx less than Vd on, my output follows input. Vx is equal to, Vout is equal to Vx. And for Vx greater than Vd on, my output voltage is equal to Vd on. Correct? These are the conditions. So for Vx less than Vd on, now let's mark Vd on. So Vd on will be a positive voltage around 0.7 over here, right? And around zero point 0.7 over here also at the input and output side. We have marked it over here. Now, what do you mean by Vout equal to Vx? Vout equal to Vx means there will be a line passing through the origin with a slope of 1. So for the entire negative half cycle, my diode will be off, correct? So for the entire negative half cycle, I will have a straight line passing through the origin, having a slope of 1. So this is my slope. Okay. Now similarly, it will continue for a small segment of the output voltage also up till VD on, because up till here, from year to year, my VD on is less than zero point 0.7. Okay. So from here, we can say if I have a dotted line over here, so the left hand side of this dotted line, I have my diode off. And on the right hand side of it, my diode D1 is on. And what happens when the diode D1 is on? Whenever the Vx greater than Vd on, then what happens? My output is equal to Vd on. That is, our output is equal to zero point 0.7 volts. So this is how we can plot the VTC curve. This is my VTC curve. So you have any doubts? You can ask me. Yeah. Anyone having any doubt? Anyone? Okay. So now let's go to this was the voltage transfer characteristics. Now let's name the clipper number 1. So since it was clipping the positive side, so this is what the clipper circuit is doing. It's clipping the positive half of the input. So it's called as a parallel. Why it is called as a parallel clipper? Because the diode is in parallel with the output. All right. Why it is called as a positive clipper? Because only positive portion of the output is getting clipped. All right. Now let's see its waveform over here. This is input output waveform. Okay. So if I have an input, let me just draw it and show it to you. If this is my input signal, let me mark it over here. So if this is my input signal, this is V in of t. We have to plot V out of t versus time. All right. So here again, I am just emphasis on fact that V in over here is Vx only. So V in of t is actually Vx of t. Okay, so what was the first condition? Vx less than Vd on. What will be my output? My output will be equal to Vx. And for Vx greater than Vd on, what will be my output? My output will be equal to Vd on, which is 0.7. Okay, so I'll mark hypothetically this line, Vd on line. So this line which I'm marking in red color is my clipping level. Okay, this is my, we can call it as a clipping level. Okay, now below this, my Vx is less than Vd on, and above this level, my Vx is greater than Vd on. Agree? Okay, so below this, my input, my output will follow my input. So as it is, as I followed the input, this is my input sinusoidal waveform, it has to be followed. And above which Vx greater than Vd on, my output will be stuck at Vd on value. So that is what we have followed. So did you all understand clipper number one? Anyone has any doubt? Quickly reply so that I can move on. Understood? This clipper? Everyone?
Yes, sir.
Okay, my Vx or V in is Vm sin omega t. Now on the same lines, what we do is, now this is my VTC curve and this is my input output waveforms. Now what do we do with the clipper circuit is as follows. Now we have connected this clipper circuit like this. The variation will be either will connect the battery in series like this, positive, negative. So we have to check whether this is assisting the clipper, assisting the diode to turn on, or it is helping the not helping the diode to turn on. Or we can connect a battery which is like this. So there are three variations of clipper circuits here only. Or what we can do is we can just replace the direction of the diode. So that diode will be connected like this. So it becomes another clipper circuit. Okay. And then we can add the two biasing conditions for the battery. So this is how it becomes 6 clippers. So let's go it quickly. We do need not explain all. We have to just determine the clipper level. So let me check. Okay. This clipper number one document is completed. Let me go to clipper number two. Now it's just a variation. We did not do anything much. So this was just a clipper number one. What was the clipping level over here? Let's write down the conditions only. What was the clipping level? Sorry, I have to increase this bit. Okay. What was the clipping level over here in this circuit? Vx greater than Vd on or Vx less than Vd on. So what was my clipping level? This is my clipping level. So this clipping level I have to find for all the clipper circuits. And once we do that, our analysis becomes very, very simple. Okay. Now let me show it to you. This was the ideal diode model. This was the ideal diode model. What is the special about the ideal diode model? In ideal diode model, my VD on becomes 0. So ideal diode model is very, very simple. You do the analysis with constant voltage model and then put VD on equal to 0. That will be your ideal diode model. Okay. Now let's go to clipper number two, I guess. Yeah. So here is the circuit. Okay. Clipper number two. Now tell me, what will be the clipping level? That V in should be less than something and V in should be greater than something. Can you tell me what will be the clipper level? So this voltage across the diode will be VD on and this supply bias voltage VP. This VD on is around 0.7 we know. Let's say this bias voltage is around 1 volt. So will it, is it helping the diode to turn on or it is making it reverse bias? What it is? Anyone? Does V in has to be greater than VD on plus VB or minus VB? If it is not helping the diode to turn on, then it should be plus VB. The V in has to be overcome this VD on voltage and VB voltage. Or if it is assisting the diode to turn on, then it should be VD on minus VB. So tell me this quickly. So let's say this is 2 volt and this is around 0.7 volt. Is it helping the diode to turn on? Come on, tell me quickly. We have to cover a lot of clipper circuits. Hello. What should be the clipping level? That's what I'm asking. Whether it's VD on plus VB or VD on minus VB. Only that much. See, in this case, is it helping the diode to turn on or it is not helping the diode to turn on? Can you tell me? So here, positive is connected, negative is connected over here. Negative, the cathode of the diode is connected to the positive of the battery. So it's making the diode reverse bias. So Vin has to overcome this voltage plus this voltage. So Vin should be, what is the clipping level? VD on plus VB. Okay. Or less than VD on plus VB. So this is my clipping level. Once you find the clipping level, the analysis becomes mechanical. It's very easy. So this is my clipping level. Are you following? Yeah, students, you have to just find the clipping level. That's it. Rest, the analysis will take care of for itself. So here is my clipping level. V in less than VD on plus VB. What will happen? The diode will be off. So when the diode is off, it is replaced with the open circuit. So here is the open circuit. My output will be equal to input. Output follows the input. Same situation. Then Vin becomes greater than VD on plus VB. Diode 1 is on. And then we have a VD on plus VB output voltage present. So here, earlier it was just a VD on. Now it is VD on plus VB if we add a bias voltage. All right. Now the waveform will be exactly similar. Only thing is the level, the clipping level has changed. See, earlier it was VD on, now it has become VP plus VD on. See over here. So in our case, it was 2 volt plus zero point 0.7. So this will be 2.7 and this also will be 2.7. Agree? And the output waveform also, earlier it was VD on, now it has become VB plus VD on. So here it is 2.7. Let's say VM is 5 volt and this is minus 5. So this clipping level is what? 2.7 volt. Exactly, analysis remains the same. Only thing is the clipping level has changed. Hello, did you all understand the analogy? This way we can switch on to clipper circuits very fast, different clipper circuits. Yes or no, kindly respond so that I can go ahead. Hello. Did you all understand the logic behind the clipping level? Yes or no? Am I audible, students? Can you all reply? Are you facing any difficulty understanding this now? Or is it clear? So this is my clipping level, my new clipping level. Okay, I believe that you all have understood that. Now, since there were no queries, now let's move on to this part. Clipper number 3. Yeah, here. So here, the biasing voltage is connected in the reverse direction. So this negative of the cathode of the diode is connected over negative over here. So what will happen over here? This is VD on. So what will be my clipping level? Can you tell me? V in should be less than equal to, V in should be greater than or equal to. Can you all tell me? In this case, this bias voltage is helping the diode to turn on. So that much less voltage I have to apply. Let's say VD on is around 0 0.7 and this VB voltage is 2 volt. So now the input requires to just cross how much voltage? 2 volt minus 0 0.7, 1.3 volt. That's it. It's not the addition, it's subtraction. So it will be VD on minus VB. Okay. Here it will be VD on minus VB. Only that is the difference. Rest of the analysis remains the same. So over here, you can see V in less than VD on minus VB, diode is off, output follows the input voltage. And V in greater than VD on minus VB, diode is on, and output voltage is VD on minus VB. Okay, the clipping level is different. It's negative actually. All right. So let's go to the circuitry. Here it is. So now the clipping level is below. Why it is below? Because it is minus VB, VD on minus VB. So what is VD on minus VB? VB is 2 volt, right? So and this is zero point 0.7. So zero point 0.7 minus 2 volt will be minus 1.3. So that's why it's coming down. Understood this? So this is my clipping level. About this clipping level, my diode is on. And below this clipping level, my diode is off. So when the diode is off, output follows the input. Okay. And here, when the diode is on, the output is saturates at minus VB plus VD on. That is why this is 1 minus 1.3 volt. So this is 2 and this is 0.7. Are you following this input output waveform? And similarly in the VTC curve, this is the VTC curve, it settles down over here. Okay, it doesn't go above. You know, in the earlier case, it was going like this, right? But this, the clipping level has gone down. Okay, so the clipping level is at the negative side. So here the voltage, for example, is minus 1.3 volt. Here also it's minus 1.3 volt. So this is my V in. This is my clipping level in this case, which I'm highlighting in blue color. So below this, my V in is less than VD on minus VB, and above this, my V in is greater than VD on minus VB. Okay, VD on is zero point 0.7, VB is 2. So for greater than, my diode is on and output is at minus 1.3. And for less than, my output follows the input. That will be a straight line passing through the origin with a slope of 1. Okay, so this is about clipper number 3. Any queries, anyone? You understanding how the analysis becomes very simple when we do it this way? Just identify the clipping level. That's it. Okay, any doubt in clipper number 1, 2, 3? And sorry, anyone? No doubts? Acha, what is the name of this clipper? It's a parallel clipper. It's a biased parallel clipper. Whether it's a positive or a negative clipper. It's a biased parallel positive clipper. Okay, because it is clipping of the entire positive half cycle. So it's a biased positive parallel clipper. All right. Now we'll go to the other variety now. Clipper number 1, 2, 3 were related. Now we have to relate clipper number 4, 5, and 6 together. So concentrate a little bit. This is a new topic which we are going to consider. Now, understand this, please. During the positive half cycle, will my diode ever turn on? So during the positive half cycle, what happens? The diode will become reverse bias. So whenever V in is greater than VD on, yeah, VD on over here is negative, like this. Do you understand this, please? So if input is in the positive half cycle, that is input is greater than VD on, my diode is always off. Okay. Now the question is, V in should be less than VD on. Okay, less than minus VD on or plus VD on. But now tell me whether it will be the clipping level will be now V in should be greater than or equal to what? Minus VD on or plus VD on? Can you tell me what it should be? It should be minus VD on, because see over here the diode is connected in reverse. All right. And output voltage is positive here, negative here. So output voltage will be also be minus VD on when the diode is on. All right. So the clipping level will be minus VD on. Just understand this. Now, in which case the diode will be on? Can you tell me this in case number 1 or case number 2? V in is greater than minus VD on. Will the diode turn on?
No.
Or V in is less than minus VD on? Will the diode turn on?
Less than.
Which case? Second case or first case?
Second.
Yes. Okay. See what I'll explain. Positive half cycle, it won't. All right. The first case, the diode is off only. Here it is off. No question of for it to be on. In the negative half cycle, the voltage, this voltage should be less than 0.7 volt for it to turn on. Similarly, we say na, in the positive half cycle, it should be greater than 0.7 volt. In a negative half cycle, it should be less than 0.7 volts, minus 0.7 volts. Then only the diode will turn on. All right. If you understand this, the next 3 clipper circuit analysis becomes very simple. We can finish it off within 5 minutes. So here, this is my clipping level. To identify this, or you remember this somehow, this is my clipping level. And to understand this, when the diode is on and off. All right. So over here, whenever V in is greater than minus VD on, we are in the positive half cycle, the diode is off. And when the diode is off, my output will be equal to the input. Okay. And whenever V in is less than minus VD on, the diode is on. Now when the diode is on, here I have to connect the wire over here like this, right? So when the diode is on, V out will be equal to minus VD on, as we have said already. Okay. Now this is again a parallel clipper, but a parallel negative clipper. Let's see how. So let us see its output characteristics, input output characteristics. Okay. So the first thing you plot is plot the clipping level. So over here, what is the clipping level? Minus VD on. So that is same as minus 0.7 volt. So below this level, what happens? V in is less than minus VD on. Okay. And about this level, what happens? V in is greater than minus VD on. Now, will you appreciate this? So we have understood that whenever V in is greater than minus VD on, the diode is off. Agree? And when the diode is off, the output follows the input. As you can see over here, the output follows the input waveform. And for V in less than minus VD on, which is V in is less than minus 0.7, what will happen? The diode is on and the output voltage stays at minus VD on. Here is the output waveform. Okay, so here is my input output waveform versus time. Did you all understand this? The clipping level. So this is the clipping level. Yeah. Okay. Now what about the input out the VTC curve? The VTC curve looks like this. See, for the entire positive half cycle, I know the diode is off, so output will follow the input. And here, what is my clipping level? This is my clipping level. Here it is, which I'm drawing over here. So on the right hand side, my diode is off. And on the left hand side of this, my diode is on. Whenever the diode is on, my output stays at minus VD on. And whenever the diode is off, my output follows the input. My output follows the input with the slope of -1. So it's a straight line passing through the origin, but now the positive half cycle and a small portion of the negative half cycle. All right. So which type of clipper circuit do you call this? Parallel positive or a parallel negative clipper?
Negative. So
Yeah, correct. Correct. It's a negative clipper because it's clipping of the negative portion of the input signal. All right, good. Now let's move on to the next one. I think clipper number 2 document is also completed. Yeah, please keep your microphones off if you're not speaking. Now, let's go to clipper number 5 and 6. Now it's a variation of clipper number 4. That's it. So you already know what before even going to the clipper circuits, what do you know? The level. Let's say VB is 0. So what was the condition? V in less than minus VD on and V in greater than minus VD on. Now in which case the diode is on? Here, V in less than minus VD on, diode was on, and here the diode was off. Now here we have to just see whether it will be plus VB or minus VB. Now tell me, in this case, is my bias voltage VB helping the diode to turn on or not helping the diode to turn on? Can you tell me? Here this is positive, this is negative. So is it assisting the diode to turn on or opposing the diode to turn on?
Opposite.
Yeah, so it will be plus or minus?
Minus.
Minus. Yes, it will be minus. In this case, see, remember, don't get confused. In the earlier case, if it was opposing, we added. But in this case, it's in a negative half cycle. All right. So that's why we are adding minus VB. Just remember that. So it will be minus VD on minus VB. Why? Because the diode turns on at negative half cycle. Okay. So the more voltage is required. So let's say earlier it was turning on at 0.7 volt. Okay. And now you are applying this VB voltage 2 volt. So now it will turn on at minus 2.7. If you say plus VB, what does it mean? It means 1.3 volt. Yes or no, which is wrong. So that's why this is correct. The clipping level over here, this is correct. So identifying this clipping level is very, very important. And now once you have identified, that's it. Please keep the microphone off, please. The meeting is getting recorded. Students.
गर्म पानी तो नहीं आ रहा था और ऊपर से स्मेल आ रहा था इसलिए बंद कर दिया स्विच गर्म पानी तो नहीं आ रहा था इसलिए वो बुला
Okay, sorry for the interruption. Yeah, so here there are two levels here. So this is my Vin greater than minus VB minus video. Now I have to don't have to explain that why it is off. So if it is off, output will be equal to input. If it is on, that is Vin is less than this level, which we have written over here, minus VB minus VD on, my output will be equal to what? Minus VD on minus VB. I hope you have understood this. So this type of clipper circuit is biased parallel negative clipper. So let's see how it is. Here it is. So remember the earlier the level was how much? Minus VD on, right? Now it has shifted down. So more voltage is required to turn on the diode. So here earlier it was 0.7. Here it will be minus 0.7 and 2. So it will be 2.7 volt. Just the clipping level has changed. So this is my clipping level, which I'm marking over here. Okay. About this level, diode is off. Diode D1 is off. Below this level, diode is on. And when the diode is on, the output voltage is at one level, minus 2.7. And when it is off, output follows the input. As simple as that. Okay. Now, similarly over here, you saw VTC curve earlier case, it was only VD on, right? Minus VD on. Now it has become minus VD on minus VP. So for this is my clipping level over here. Let me just highlight the clipping level. It's very important to understand the clipping level. This is my clipping level. Okay. So below this, my diode is on. Greater than this, my diode is off. If it is off, output follows the input. But so we have a straight line passing through the origin, extending to the negative half cycle also. And if my input is less than minus VD and minus VB, my diode turns on. Okay. So yeah, actually based on this, it is called as a biased parallel negative clipper. All right. I hope it is clear. So now let's go to this clipper number 6. The battery is reversed now. So what will happen? This is positive. This is positive. So VB voltage is helping the diode to turn on or opposing, helping now. So let's write down that condition for the reverse diode. So V in greater than minus VD on, less than minus VD on. So in this case, we know it is off. Diode D1 is on. And in this case, it is off. We have to just determine whether it's plus VB or minus VB. Tell me whether it's plus VB or minus VB. I'll just give you a hint. If this is minus VD on, just check from minus VD on, this will be plus VB directly, automatically, if you go do the normal analysis over here. So uh, if it is assisting the diode to turn on, that means let's say it is plus VB and here it is plus VB. So VB over here is how much? Let's say 2 volt. This is around 0.7 volt. Okay, so it is helping the diode a lot. So it is minus 0.7 and plus 2 volt. So 1.3 volt. So Vin should be greater than 1.3. Vin should be less than 1.3 for that clipping level. So this is my clipping level over here. So this is the clipping level. Okay. Once we identify the clipping level, entire analysis becomes very simple. Now we have to just write this VD on minus Vin greater than minus VD on plus VB. Diode is off. Diode is off. Output follows the input voltage. All right. And whenever the input is less than minus VD on plus VB, diode is on and output is equal to minus VD on plus VB. Okay. If VD on is 0.7 and this is 2, this will be 1.3 volt. All right. So this type of clipper circuit is called as biased parallel negative clipper. Now let's see its input output waveform. Don't be surprised why it is going up. Anyone can tell me why this level is not down? So let's take an example. If this is 0.7 and this is 2 volt. So 2 minus 0.7 will be 1.3. So therefore the clipping level will be positive. Okay. Understood this? If Vm is 5 volt, this will be minus 5. So therefore the clipping level will be above. So this is my clipping level. All right. So above this clipping level, my diode D1 is off. And below this clipping level, my diode D1 is on. And when the diode is on, the output is equal to that clipping level, which is plus 1.3 volt. And above that, if Vin is greater than plus 1.3 volt, my diode is off and output will follow the input. Got it? Now here is my VTC curve on the similar lines. Since my clipping level has changed now, here is, let me highlight the clipping level always. So here is my clipping level. If input is greater than this clipping level, input is greater than minus VD on plus VB, my diode will be off. Here my diode is off. Okay, and output will follow the input. We have a straight line passing through the origin, and for this case my diode will be on. For V in less than minus VD1 plus VB, my diode will be on, and my output will be stuck at minus VD1 plus VB, which is around 1.3 volts, which we have determined, right? For example, if VB is 2 volt. Okay, have you all understood this clipper circuits? So clipper number 4 to 6 are related. Clipper number 4 to 6 were the same category of negative clippers. Have you understood this? Can I move on to the next topic now? Yeah, students. All right. Let's move on to the next circuits. All right. Let's move on to this now. We have whenever we have two diodes in a clipper, it's basically a two-level clipper or a combinational clipper. Okay. So here there will be two conditions. All right. Now, let's say this voltage across the D1 is VD1 on and this will be VD2 on. Now, you all tell me now how we should proceed here. You have two levels, two diodes. So here it is, what should be V in? So V in should be great. When will the diode D1 turn on? Can you tell me? This is VD1 on.
VN is greater
When,
than VD.
yeah, V in is greater than VD1 on, then my diode D1 is on. So whenever Vin is greater than VD1 on, now this voltage is again in parallel to this diode also. So is this diode on when under this condition? No. So we can say D1 is on and D2 is off. All right. And when is the diode D2 getting turned on? So here the voltage over here will be plus minus VD2 on. Can you all tell me? Vin less than minus VD2 on. Understood this? Whenever Vin becomes less than minus VD2 on, my diode D2 will be on. So diode D2 will turn on and D1 will be off. So if you have understood this, then the entire analysis becomes simple. So did you all understood why I have written this way? Because individually I know how does the diode turns on. So for D1, if Vin is greater than VD1 on, let's say VD1 is 0.7 and this is minus 0.7 VD2 on. So whenever Vin is greater than 0.7 volt, my diode D1 will be on. And whenever my input is less than minus 0.7, my diode D2 will be on. All right. So when one diode is on, other will be off. Okay. So in the case of two diodes, we need to find the point at which they turn on. So where it will turn on, Vin greater than VD1 on, that D1 is on and D2 is off. So D1 is on, D2 is off means open circuit. So what will my output voltage? Output voltage will be VD1 on in this case. Okay, constant and equal to VD1 on. Now, whenever input is less than minus VD2 on, my diode D2 is on and D1 is off. So in this case, my output voltage will be equal to minus VD2 on. This much you have understood. Hello? This you have
Yes, sir.
understood or what? Okay. But what happens? So let's say, let me uh, take you over here. So there are two clipping levels over here. One is over here. Let me draw it. So I'll draw this and understand. I'll show you the output and then I'll explain how this has come. So these are my two levels. Just hold on a bit. And this is my second level, the red level. So I have two clipping levels over here in this case. This is clipping level number 1 for diode D1. This is clipping level for diode D1. And what is the red color indicates? Clipping level for diode D2. Okay. Now, if Vin is greater than, or sorry, less than minus VD2 on, my diode D2 turns what, on or off? On. And whenever less than, and whenever my input is greater than VD1 on, my diode D1 turns on. Okay, for less than it, it is off. So when is my diode off? Diode D1 is off when over here, right? And D2 is off over here, right? So this is diode D2 is off, and here diode D1 is off. What happens in this level? So whenever Vin is less than, whenever Vin is less than VD1 on and Vin is greater than minus VD2 on, what is happening over here? I'm asking what is happening between these two levels. What about the state of the diodes? Both are
diodes
off. Why?
Yeah.
See, yeah, correct. Absolutely correct. Both the diodes are off. How? Because Vin becomes less than VD on, so that D1 will be on below this. And above this, Vin is greater than minus VD2 on, so diode D2 is also off. D2 is off for above this line. So let me highlight it. D1 is on, D2 is off for below this line. See, the D1 is off. So above this line, which I'm drawing over here, below this line, D1 is off. So over here, D1 is off. And what about D2 off? D2 is off above this line, right? Above this line. So which is the common point? This is the common point when D2 is off. So let me just remove these lines now for somewhat clarity. Okay. So I hope you have understood. So in between these two regions, that is whenever Vn is less than Vd1 on and greater than minus Vd2 on, my both the diodes will be off. Okay, so here I've written over here, whenever Vn is less than Vd1 on and greater than Vd2 on, diode D1 is off and D2 is off. So whenever this happens, my output follows the input. Okay, so let's see if it is follows the input or no. Yeah, it is following. See, whenever Vin is less than VD1 on and greater than VD2 on, my diode is off. Both the diodes are off and output follows the input. About this, Vin becomes greater than VD1 on, my diode D1 is on and output is stuck at plus VD on. If it is below this, Vin is less than minus VD2 on, my diode D2 is on and output is at minus VD2 on. Here it is. So these are my, this is clipping both positive portion of the input signal and negative portion of the input signal. That is why this type of clipper circuit is called as a combinational clipper or a two-level clipper. Combinational clipper circuit. Now, how will be my input voltage transfer characteristics? See over here. So I have two levels, as I've already told you. Here it is, level number 1. Okay, input level I want to plot now. Yeah, this is input level. So this is first level, this is second level. So over here, my D1 is on. Over here, my D2 is on. And in between these two, my D1 is off. D2 is off. So in between these two, when both the diodes are off, output follows the input and we have a straight line passing to the origin. Okay, beyond this, whenever Vin becomes greater than VD1, here it is VD1 on, my diode D1 is on, and output is stuck at VD1 on. And whenever input is less than minus VD2 on, my output is stuck at minus VD2 on. So this is my VTC curve of this combinational clipper. Understood this? I know I am a little fast, but have you understood the logic? We have to just find the clipping level. That's it. Everyone understood this?
Yes.
Okay, great. So if you have understood this, you will understand slight modification now. So it's the same circuit, only the biasing voltage are added. So let's write down the voltages of the levels, clipping levels first in general. Let's consider VB1, VB2 will be 0. So V in is should be greater than VD1 on for the diode D1 to turn on, correct? And V in should be less than minus VD2 on for the diode D2 to turn on. Now what it should be, whether it should be plus VB2 or minus VB2, let's find out. So here, let's consider VB1. So is VB1 helping the diode to turn on or not helping the diode to turn on? Here it is negative, here it is positive negative. VB1 is opposing, so it will be plus or minus. It will be plus VB1. Understood this? Because that much voltage you have to overcome to turn on the diode. Yes, if it is opposing. What about D2? Is VB2 helping D2 to turn on or off? It is helping it to make it reverse bias. So that much extra voltage you require. So here it is minus VB2. Understood this level, everyone? So let's say VB1 is equal to VB2 is equal to 2 volt. And VD1 on and VD2 on is 0.7 volts. So this clipping level will be 2.7 volts. This clipping level will be minus 2.7 volts. Understood? Because VD on is 0.7, VD2 on is also 0.7 volt. Okay, that's it. And whenever Vin is less than this or Vin is greater than this, then both the diodes will be off, as we have discussed. So see this clipping level. If Vin is greater than VD1 on plus VB1, diode D1 is on, D2 is off. And output is equal to what? VD1 on plus VB1. See here, VD1 on plus VB1. So if this is 2 volt, this is 0.7, that will be 2.7 volt. Okay. Now similarly, if input is less than minus VD2 on and minus VB2, that means input is less than minus 2.7 volt, my diode D1 is off, D2 is on. And D2 is on means what? Output is equal to VD2 on minus VD2 on minus VB2. So this will be minus 2.7. Okay. So what in summary? In summary, what can we say? If V in is, let me write it over here. If V in is greater than 2.7 volts, my diode D1 is on. Okay. If V in is less than minus 2.7 volt, my diode D2 is on. And if V in is less than 2.7 volt and V in is greater than minus 2.7 volt, my diode D1 and D2 are off. So just we are increasing the biasing level. That's it. You remember last time over here we had only VD1 on and VD2 on. Now this level has raised. So level has become 2.7 and minus 2.7. Rest the analysis remains the same. Where is my clipping level? This is my clipping level now. This is my new clipping level. I hope you are following this. So these are my clipping levels. So here V in is greater than 2.7 volt. Diode D1 is on. Over here when it is less than, V in is less than minus 2.7 volt. That means D2 is on. And in between that, what happens? D1 and D2 are off. So D1 is off, D2 is off. Okay. I hope it is clear. The same thing is reflected over here in the input output waveform. How will be the input output waveform? I have not drawn it. Here it is. Here it is. So the clipping level has increased. Earlier it was VD on. Now it has become VD on plus VB1. So these are my two clipping levels. Here it is. Let me always draw the clipping level. So beyond this, Vin is greater than 2.7. Example I'm giving you. VD on is 0.7, VV1 is 2 volt. And we have one more level. This is for diode 2. If it is less than it, Vin is less than 2.7 volt, your diode D2 will be on and your D1 is on. Okay, and in between what happens? In between these levels, whenever Vin is less than 2.7 volt and greater than minus 2.7 volt, both the diodes will be off and output will be equal to input. So output is following the input. If it is input is greater than 2.7 volt, output will be stuck at 2.7. If input is less than minus 2.7 volt, output will be stuck at minus 2.7. So this is called as a biased combinational clipper or a biased two level clipper because it is clipping both positive and negative portion of the input waveform. Did you understand this now? Clipper number 7. Everyone clear about this? Hello. Any doubts? Come on, reply fast so that I have to cover the next topics also. I have pending clipper circuits. Any doubts over here in clipper number 7? Yeah, students. All right. Let's go to the next clipper circuits. Now we come to the category of series clipper. So over here, as you can see, the diode is no longer connected in parallel with the output. So here the analysis is slightly different. So pay attention now for clipper number 8. Okay, ready for this? Are you ready? Everyone? Okay. So now tell me, when does this diode turn on? What is the condition or what is the clipping level over here? V in greater than this voltage. This voltage is VD1, which is VD1 on. Okay. So whenever Vin is greater than VD1 on or Vin is less than VD1 on. Tell me what, in which case the diode turns on? First or second? Hello? Here the diode is on and here the diode is off. Okay. It is quite simple. The clipping level is very, very simple. So this is my clipping level. But in series clipper, you have to be careful in the analysis now. So this is clipping level. All right. Let me show it to you how. So let's consider this diode D1 is on for V in greater than VD on. That is very clear cut picture, but the circuit get reduced to this. So see over here, we have V in, we have VD on. So this is plus minus VD on. And what is my output? My output is not equal to VD on now. Output is something else. So we'll apply the KVL around this loop. We get minus VD on minus, or we can say here the equation is slightly this way. We can write it as plus VD on. Okay. Then this will be minus VD on minus V out. Okay. It change little change in the polarity in this direction. So what will be V out equal to? V out equal to V in minus VD on. Same thing only. Okay. Now it is clear. So output is equal to input minus VD on. Did you all understand this? Now comes the concept of tracking. So it means output voltage V out tracks V in, but with a shift of VD on. Now, why this is possible? I mean, how this is possible? Can you tell me? How we can do it? This you have understood, it should be V in minus VD on. So there is a concept of tracking now. Yeah, output. See, if it was directly V in, we would have written output follows the input. But here the output follows the input, but with a shift of VD on. What does that mean? We are not calling it follows directly, we are calling it tracking. So output is tracking the input, but with a shift of VD on. I'll explain this over here, over here. Okay. So let me show you. Let me directly go to this voltage transfer characteristics. Let me build this line. This is my clipping level. Okay. So let's say, let me show it over here. So this is my V out. This is my V in. So if my output was equal to V in, what it will be? A line passing to the origin, right? And whenever for V in greater than, let's say VD on, for V in greater than VD on means V in greater than 0.7, my diode was on. All right. VD on, V in greater than VD on, my diode D1 is on. So for here, how do we plot the curve? So here it was VD on, this is around 0.7. This would have been my clipping level. And how will I plot the output? I mean, how will I plot the inputs waveform? Output waveform over here, this passing to the origin, and then it will be a straight line, correct? And here, my output level would have been like this. You agree? About this level, my diode is on, my diode will be on. Okay, oh, sorry. Opposite I said. Here it will be like this, and here it will be like this, correct? So for my input, here it is on, and here it is off. That D1 is off. But now what is happening is, if my input, now let me just erase this picture for y'all. Okay. So now what I'm saying is, for a tracking purposes, what is this? So do you have a scenario over here? If my output V out follows the input, okay, we say follows just the input V in. So if this is my V out, this is my V in the positive half cycle, let's consider a positive half cycle. So we can say that it's passing a line passing to the origin directly. Okay, straight. So this line is called as V in, V in. Now I am saying output follows V in with a shift of VD on, with a shift of minus VD on. So how will you plot this line? So what does a shift of minus VD on means? I should plot it below this or above this? Can you tell me? Same nature of the graph, but whether it will be, I should consider above this or below this. This minus VD on, where it will I plot?
Below.
Yes, why? See here, I hope you are understanding. V in is a continuously varying signal like this. And now I'm saying it's V in minus VD on. That means over here, are you understanding? This is going from 0 to 5. Now it will go to, you know, V in minus VD on, right? So minus 0.7 to something else. So this level will be shifting down. So earlier I have this level, this was V in equal to V out. Now it will be something else. The level is shifted down. That's it. This level is shifting down. So if this is V in, where will be V in minus VD on? So you have to plot over here, VD on. Okay. This is VD on line. Where will I plot Y intercept? See, basically you understand this now. Y is equal to mx plus c. Yes or no? So what is Y over here? V out. What is M? M is slope 1. So this is equal to V in. And what is my Y intercept? Minus VD on. Are you understanding now? Where is my Y intercept? Minus VD on. So here it is minus VD on. So there will be a line from here, passing from here, and parallel to this line. It will be parallel to this line. So this line is V in minus VD on. Did you understand this? Yeah. This is Y intercept. Y is equal to mx plus p c concept. Huh? M is 1 over here. So this is my Y intercept. My y-intercept is minus VD on. So if I take a line, draw it parallel to this. So this is exactly parallel to this, but this is V in, so this will be V in minus VD on. If I have to draw V in plus VD on, then how would I have drawn? If it was V in equal to V out equal to V in plus VD on, then how would I have plotted it? Anyone? Here, where what is my y-intercept? Y-intercept C will be plus VD on. So I can see over here like this. This was VD on. Okay, so I would have drawn a green line. Let me use green color like this. So it will be a same line parallel to the V, but this will be V plus VD on. Okay, understood this now, everyone? So we can say that is why the concept of tracking comes. It means output voltage, this is output now, V out tracks the input with a shift of, but with the shift of minus VD on. In this case, that's why the meaning of this lines. So output is V in minus VD on means it's slightly tricky. We have to draw it this way. So here it is. This is my level, clipping level. Below this, my diode is off. So it will be a line. I mean, yeah, when the diode is off, let's see what happens. Here is the diode is on. When the diode is on, what happens? The output tracks the input, but with a shift of my VD on. Okay. So let's discuss now. So I hope this concept is clear. The concept of tracking is clear now. The output tracks the input, but with a shift of VD on. Now, when the input is less than VD on, my diode is off. And when the diode is off, my current in the circuit is zero. So my output will follow the input. Will my output follow the input over here? That is my question. No, because your input is disconnected because the current flowing through it is zero. So what will my output will be? Zero. Did you understand this? For the first time, the output is becoming zero. Did you understand this? If Vin is less than VD on, my diode is off. This becomes open circuit. My input is disconnected from the output. So hence my output will be zero because no current flows through this register. So for this case, for diode off case, my output will be zero. See, highlighted by this point. It is zero over here. Clear about the VTC curve? For input greater than VD on, my output tracks the input, but with a shift of minus VD on. And for less than it, for input voltage less than 0.7, your diode voltage is zero. This is where the confusion of the students happened in series clipper circuits. Okay. Now let's go to the input output waveform now. Same thing over here, right? Okay. So see over here, first of all, here how to plot this waveform, let me tell you. Let me just tell you. So first of all, draw the input waveform. Obviously, you will draw the input waveform like this. Acha, this is which line? This is V out or this is V in line, right? Now I have to plot V in minus VD on. So where will I go? This, here my level is zero level. Here my level is 0 volt level. And now if I have to plot a line which is plotting V in minus VD on, then my level has changed. Now my level is minus VD on. So this is minus VD on. Now I have to start from here. Let's say my zero level has gone to minus 0.7. So I have to start from here like this. I'll draw a dotted line and my entire waveform is shifted down like this. So what is this line? This line is this. This is input line. This is V in minus VD on line. Did you understand? So at every point, there is a difference between minus 0.7 here. Are you following? Yes or no? So this is also 0.7. This is also minus 0.7. So where is my clipping level over here? What is my clipping level over here? VD on. So here, if my output, if my output, if my input is less than VD on, input less than VD on means what? Here it is less than VD on, my output will be zero, straight away zero. So I have to actually plot this as the output, this as the output, this one. Okay, so what it is saying, this is my reference now. The red one is my reference. What it is saying is I am using blue color now to plot the waveform. So this is the level now. Okay, so this is the clipping level. Video on. Here it is, V in level. So if input is less than video on, okay, if input is less than video on means what? For this line, for this curve, for the red one, when is input less than video on? This is video on, right? Here it is 0.7. So where it is starting from? Over here. Okay. So below this input is less than video on over here. So output will be 0. If input is greater than video on, my output follows V in minus video on. So output will follow V in minus video on. See this line over here. Again, it becomes less than that. Then again, it will be a straight line. Now here in a negative half cycle, again, it will be 0. And then again, it will follow this waveform. Okay. That's how you get this. This slightly tricky, but you have to do it this manner. So this is my clipping level here. In this case, minus VD on is my new level for this orange color waveform, which is V in minus VD on waveform. So with respect to V in minus VD on waveform, we have to consider now. With respect to this waveform, the red color one, we have to consider. So for any input voltage is greater than this, my diode is on and my output will follow V in minus VD on curve, which is this orange color curve. Okay, and for less than that, for less than VD on, it will be a 0. Output will be 0. So this is how the input output waveforms looks like for clipper number 8. Did you all understand this clipper number 8? Because it was very crucial to understand this. Hello, you have a doubt still about the tracking level, or it is clear now? Hello,
Clear.
students, clear it is?
Yes.
Okay. Let me see if I can show you some simulation waveform for this. This is clipper number 8, right? Clipper number 8. Yeah, this is the clipper number 8, right? Let me show you the input output waveform. So the input is a sinusoid. See how my output will be. Understood? Same as this which we have plotted, right? This is same, if you can see. Correct? Understanding? So whatever we are doing, it's realistically existing. Here it is. Exactly the same. Okay, fine. Understood this? Can we move on to the next one now? Clipper number 8, 9, 10 will be same, almost similar. Just the clipping level will keep on changing. Okay. Now now what will be the variations? Addition of a battery here, like this. First case, this will be clipper number 9. Then second case, it will be reverse. And then the diode will be reverse and again 2 batteries. So remaining 5 circuit analysis will become very simple. Will take 5 minutes to understand that. Now, tell me, what is the clipping level? I mean, what is the condition? V in, let's say VB is 0. So for VB 0, V in greater than plus minus VD1 on, correct? So VD1 on, when V in is greater than VD1 on, V in less than VD1 on. When is the diode on? Over here. Diode D1 is on over here. Diode D1 is off over here. Now tell me whether it should be plus VB or minus VB. Is it assisting the diode to turn on or it is opposing the diode to turn on? Negative connected to positive. So it's reverse biasing the diode. It's opposing the diode to turn on. So whether it will be plus or minus, come on. Plus VP. Input has to overcome this diode voltage plus this voltage. So let's say if it is 0.7 and this is 2 volt. So V in has to be greater than 2.7 volt. Okay. And here also it will be, here V in should be plus. Here also it should be plus. If Vin is less than 2.7, my diode will be off. Okay. Now let's see this, applying constant voltage model. When Vin is greater than VD on plus VB, as we have said, diode D1 is on. But here V out is not equal to VD on. It's not a parallel clipper. Parallel clipper are very easy. So here we have to apply the KVL. Again, the KVL, this will be minus plus V in. Here it will be minus VD on minus VB minus V out equal to 0. Correct? This is rise in potential. So plus V in, fall in potential because plus minus plus minus. So V out will be equal to V in minus V out will be equal to V out goes on that side, V in minus VD on plus VB. Earlier you remember it was V in minus VD on only. Now this level has increased. Let's say this is 0.7. This has become 2. This will become 2.7. So the same concept of tracking happens over here. Okay. That means the output tracks the input, but with a shift of earlier it was 0.7. Now it is 2.7. That's it. Remaining concept remains almost the same. So let's say what happens when the V in becomes less than VD on plus VB. So diode D1 is off. When a diode D1 is off, my input is disconnected from the output and no current flows through the resistor. My output voltage will be 0. Correct? Understanding or no? Yes. So now see, this level has shifted, right? So this was V in line, VTC cover. This is which line? V in is equal to, V out is equal to V in minus VD on plus VB. Just we have added a VD on, we have added to VD on a VB voltage. That's it. And this is my level, clipping level. Let me draw the clipping level. Here it is. This is my clipping level. So about this, my diode is on. When a diode is on, output tracks the input, but with a shift of VD on plus VB. So there is a difference between V in and V out. It's again a parallel line. Okay. And with respect to this line, you have whenever V in becomes less than it, my diode D1 is off and my output is 0, straight away 0. So this is my VTC curve. VTC curve is simple. Input output characteristic is slightly tricky. Can we move on now to input output characteristics? Okay. So what the first thing you draw? First thing you draw is this V in line. Then you draw, what will you draw next? V in minus VD on plus VB line. So let's say this VM is around 5 volt. This is around minus 5 volt. What is VM minus VD on plus VB? Can you tell me? This is VM, na? VM. So it will be VM minus VD on plus VB. Let's put some numbers. If this is 5 minus 0.7 plus 2. So 5 minus 2.7 to how much it is? 2.3. So that's why this level is 2.3. Are you understanding? And what about this level? What about this level? This level will be even greater. So anyways, this is the line. This is minus 2.3. Okay, 2.3 minus 2.3 to 3. 2 point plus 2.3. This will be my level. So how will I draw it now? How will I draw this waveform? How will I draw it waveform? How will I plot this line? V in minus VD on plus VP. So this is V in, right? This is starting from 0. Okay. Whenever V in becomes 0, calculate this level. It will be minus 2.7, right? So this point will be minus 2.7. So minus 2.7 with respect to minus 2.7, this is the clipping line now. With respect to minus 2.7, you will draw a sinusoidal waveform like this, the orange color one, with respect to this, the gray color input waveform. So this waveform is V in minus VD on plus VP. Are you understanding? And this waveform is just V in. So it is tracking my out, the V in minus VD on plus VB is tracking the input, but with a shift of 2.7, minus 2.7. Okay, so entire waveform is shifted 2.7 down. Now the output will come on this orange curve only. So what are the conditions? Vin greater than 2.7 volts, right? And Vin less than 2.7 volts. Yes or no? This will be, I think, 2.3, right? This level is 2.3. Okay. Now, which level we are talking about? 2.7, 2.7 volts. Now, this is my new clipping level. This is my new clipping level. And which input waveform I'm talking about? Now, this we have to draw with reference to this now. So whenever input is less than, minus 2.7, so that means here, over here. If it is less than that, then output will be 0 from year to year. So you have to calculate this level now. This level also will be 2.7. It's 2.7. Okay. So this is the level which we can plot. I'm not plotting here, but it will create too much confusion. So input is greater than that. Input is greater than that. My output will be tracking the input, but with a shift of VD on plus VB. So this orange color line, it will follow. And if it is less than that, if input falls below this 2.7 volts line, then my output will be 0. So output will be 0 entirely over here. Okay, it will only track whenever my input becomes greater than this. Are you understanding? Hello? This somewhat input output waveform is slightly trickier. Rest from this curve, you have to transfer this to this curve. Let me show you the waveform for this. This is clipper number 9, I guess. Let me show you the input output waveform for this. Here it is. See the level. And this output voltage is just this voltage. This orange color line is just for your reference, for your tracking. This is my tracking line. Okay, so this is how the output would. Now this level will be above or below based on VB. We have considered VB to be 2. Here we have considered VB to be 1 volt. So it's fine. So accordingly, this level will change. Okay. So clear about this clipper number 9, everyone? Okay. Now we go to clipper number. Again, 9 has come, I think 6. Yeah. Clipper number 10. Reverse entirely. Now this will be the reference only with reference to what we have done before. So tell me what will be the level now over here. Come on. We have done enough clipper circuits. Tell me the level. If VB was not present, then Vin greater than VD1 on, Vin less than VD1 on. Let's quickly wind it up now because you have to cover clamper circuits also, 2 or 3 of them. Here the diode D1 will be on. Here the diode D2 will be on. So let me help you out. This is plus minus and this is minus plus. So VB is helping the diode to turn on, right? It's assisting. So it will be minus VB. So this will be my level, comparison level. Okay. Understood this? Now let's go over here. See, Vin greater than VD1 minus VB, the diode is on. And when the diode is on, is replaced with a short circuit with VD on. And you apply the KVL over here, what you will get plus Vin. This is plus Vin minus VD on plus VB. Here it is minus VD on because it is fall in potential. Here it is rise in potential. So again plus VB minus V out is equal to 0. So V out will be equal to V in minus VD on minus VB. See the clipping level as only the shift is changed now. That's it. So again, there will be a concept of tracking. All right. Let's say VD on voltage is 0.7 and VB voltage is around 1 volt. Right. So it will be V in minus this 0.3 volts now, less, the shift will be less. So it means that the output voltage tracks the input, but with this shift, VD1 minus VB. Okay. Now if Vin becomes less than it, Vin becomes less than VD1 minus VB, diode D1 is off, output is equal to 0 because no current flows to the resistor, the input is disconnected. So output is 0. Analysis becomes simpler. Now plot the VTC curve. See, this is my VTC curve. Haven't I told you VD on minus VB will be over here above? I told you all that, right? This is plus VB. Yeah. Plus VB will be below, minus VB will be above. Understanding or no? So here if you find the y-intercept will be minus VD on plus VB. If you just open this bracket, it will be V in minus VD on plus VP. So this is my y-intercept. So this will be the line parallel and this will be my clipping level over here. VTC curve is simpler to draw. On the right hand side, my diode is on. On the left hand side, my diode is off. Okay. V in greater than VD on minus VB, V in less than VD on minus VB, diode on and off. VTC curve is quite simple. If it is off, it will be 0. If it is on, it will be follow this new line. V in this line is V in minus VD1 minus VB. Okay. Now drawing the input output, I hope it is clear this. Now drawing the input output waveform, it's quite a challenge. Now this orange color waveform which I have drawn up, first I have to draw that because it is VM minus VD on minus VP. So this will go above. So if I treat this V in as 0, finding this level. If I treat this V in as 0, okay, so what it will be? Minus VD on. VD on is 0.7, let's say, plus VB. So let's say this VB is 2 volt, let's say. So what will be the level now? 1.3. That's why it's coming up. So with respect to this green color, can you see this green color? Green color will be the new level for this input waveform. So this waveform is V in minus VD on minus VB. Draw this input waveform. Okay. Now this will be the level. This will be the level. If V in becomes what was the level? V in becomes greater than, let's say this is VD on minus VB. So VB is, let's say, 2 volts. So it will be, yeah. So let's say this is that level which we are talking about. Now about this level over here, when we say V in greater than VD on minus VB. So what is VD on minus VB over here? Let's say VB is 2 volt. Let's consider VB as 2 volt only. So this is 2 volt. How much this will be? 1.3, right? Minus 1.3. Yeah. So VB is 2 volt. So V in has to be greater than VD on minus 2 volt. That is 0.7 minus 2. So that will be minus 1.3 volt. Or V in less than minus 1.3 volt. Here the diode D1 is on and here the diode D is off. So whenever it is on, output will follow the input. So here it is this level. See this level, the green level. The green level is my clipping level now. Okay. So about this, my diode D1 is on. Now output will follow the distinct level. V in minus VD on minus VB. And below this line, now V in less than minus 1.3 volts. So V in less than minus 1.3 volts means what? Below this. So this is 1.3. See, this is 1.3 volt. So V in is less than 1.3 means over here, not over here. Are you understanding? V in greater than that, but V in less than minus 1.3 means this level. Because we are considering V in to be 0 over here, let's say. So this will be 1.3, minus 1.3. Are you understanding? It is shifted below. It is, that thing is shifted above, so this is also shifted below. So below this level, my diode will be off and my output will be 0. About this, it will follow the input, but with a shift of VD on minus VB. I hope you're following this. Yeah, students? You're there with me? Hello? Yes or no? Little bit you're following? Just a reply will ease my queries. You're finding any difficulty in understanding these clipper circuits? Anyone? We are almost on the verge of completing clipper circuits. So, okay. Can we move on to the another last category of clipper circuits? That's it. 11, 12, 13. 13 clipper circuits are there. Now we have reversed the polarity of the diode. That's it. Now, can you tell me what will be the level now? When does the diode turn on? Anyone? Anyone? When does this diode turn on? Will it turn on in the positive half cycle? Yes or no? No, because the diode will be reverse bias. So when it will turn on? It will turn on when input is less than minus VD on. And if it is off, if input is greater than VD on. I think we have discussed this. Diode is off, diode is on. Correct? So whenever input is less than minus VD on, diode is on. The circuit will reduce to this network. Now the KVL around the loop will be, here it will be plus V in, here it will be minus VD on and minus V out. Okay, so V out will be equal to V in plus VD on. Okay, so again, there will be a concept of tracking. Your output will track the input, but with a shift of VD on. Now this shift is above. The shift is above. Yeah, plus VD on. Actually, the shift is above. So here is the shift here like this. It will be a line parallel to V in line. So V in plus VD on line will be over here like this. If this is V in, this will be V in plus VD on. The tracking is above. So this difference is VD on. Understood? Yes or no? So V out is equal to V in plus VD on. If I write it as Y is equal to MX plus C, so M is 1, Y is this, X is this, and Y intercept is VD on plus VD on. So Y intercept is plus VD on is over here. This is around 0.7, let's say. So this is correct. Whatever drawn is correct. Absolutely correct. Now let's understand this further. Input is V in plus VD on when the input is less than minus VD on. So input is less than minus VD on means what? If this is my level, so input is less than minus VD on. My diode is on here. So that's why it will follow the output, but with a shift of V in plus VD on. And when it is on this side, when the diode is off, my output is zero, straightforward zero. So in a series clipper, when the diode is off, the output is zero, straightforward. So output is zero. Let's see. If V in is greater than minus VD on, my diode is off. And when a diode is off, input is disconnected from the output and output is equal to zero. Okay. So this type, it is clipping of the positive portion. So that's why it's called as a positive series clipper. Earlier one, what we have studied was a biased positive series, negative clipping, negative series clippers. Okay. Now, this is a challenge. Everyone listen very, very carefully. First of all, for the input output waveform, draw the input waveform with respect to zero. Then draw the new clipping level, it's VD on. Okay. Now we have to draw V in plus VD on. So here V in substitute zero. What do you get? VD on. So VD on is my new clipping level. This is my clipping level now. Just remember this. This is my new clipping level. Okay. For this waveform. For this waveform. Okay. Now V in has to be less than minus VD on. So what is the condition? V in less than minus VD on. Diode will be on. V in less than, oh, greater than minus VD on, diode is off. When the diode is off, it is zero. So till where to where it is 0? For till year to year it is 0. Why it is 0 up till year? Because at this point, V in, now this is my V in plus VD online. This is my V in, this is my V in plus VD online. And what is this line? V in line. Okay. So when I'm talking about here, V in is greater than minus VD on. So if this waveform, the orange waveform, this is VD online. So let's consider this as a reference now. Let's say my output waveform is starting from here only. I mean, we have to plot in the orange waveform only, basically. So here, if I go below by 0.7, here there is a difference now. This is point VD on, difference is there. So input is below minus, greater than minus VD on. So what will happen? My output will be 0. See here, at this point, at 0 point only, the output will be 0. And it is less than minus VD on, less than means it's below this also. Then what will happen? My output will follow V in plus VD online. So output will follow this orange curve. Understood this? Yeah. The input output waveform with respect to time for, and here you can see the entire positive half cycle is getting clipped. So that's why it's called as a positive clipper. I hope it is clear. Now just we have to add the battery. That's it for clipper number 12 and 13. So let's finish it off first. Clipper number 12 and 13. Here it is. So clipper number 12, quickly write down the clipping levels. Here we have a battery. Now is it assisting? This is positive, negative. This is negative, positive. No, it's not assisting. So V in, when the diode is on, which is less than minus VD on, then the diode is on. Correct? And here V in is greater than minus VD on, then the diode is off. Now whether plus or minus will come. Come on, tell me. Hello. What will come over here? Yeah. Plus will come or minus will come? It will be plus, now. Plus. VD on minus of VD on plus VP minus of VD on plus VP. So when the input is less than minus VD on plus VP, because you have to overcome this much voltage, right? So diode D1 is on. Here it is. Here the first condition is when a diode D1 is on, the circuit gets reduced to this network. So it will be plus V in plus VD on because rise in potential. Then we have again plus VP minus V out is equal to 0. So V out is equal to V in plus VD on plus VP. See here, it will be plus VD on plus VP. Last time it was VD on, right? Now we have to add just VP. That's it. So earlier the level was 0.7. Now it becomes, let's say, 2.7. So earlier it was 0.7. Now it becomes 2.7. That's it. Okay. And whenever it is greater than this level, the diode is off and output is equal to 0. So let's quickly see this. This is the transfer characteristics. Earlier it was what? Earlier it was like this, right? So this difference was how much? Earlier this difference was VD on. Now it has become VD on plus VP. That is 2.7 volt. So here the y-intercept also will be 2.7 volt. And then we get this line, this stacking line. So this is V in equal to VD on plus VP. V in equal to VD on plus VP line. Okay. I hope it is clear now. So what is my level now over here? So what will be the level over here? If V in is less than minus 2.7. So this is that 2.7 volt, minus 2.7. If V in is greater than minus 2.7. So here it is on. So it is on over here. Diode is on over here. And here it is off. Okay. Let's transfer this to VTC, to the input output characteristics. Here it is. Now,
just substitute V in plus VD1 plus VB curve. Here substitute V in equal to 0. So what is my level now? VD1 plus VB. So VD1 plus VB, this is 2.7 volts line. Okay, with respect to that, draw this waveform. First of all, draw the input waveform, the gray color. Here the input output won't be there. Output will be there at this level, the orange color line. So take 2.7 volts up and draw this line, orange color line. Okay. Now, what are the conditions? V in less than minus 2.7. So this is 2.7. Here it will go, it will be minus 2.7. So V in greater than minus 2.7, output will be 0. So here it is 0. If it is less than that, then output will follow this orange color curve, which is V in plus VD on plus VB line. Are you understanding? Hello? You're following this? Yeah?
Yes.
Now, now let's go to.
I hope you are able to hear me. Yeah, let's go to the last clipper circuits, then we'll wind up this topic quickly. Now, this VB is helping the diode to turn on because this is plus minus, this will be plus minus, so it's helping. So how will you write this? First of all, VB is 0, how will you write this? V in less than minus VD on, and here it is greater than minus VD on. In the first case, the diode D1 is on. Second case, the diode D1 is off. So how it will be? Minus VB. Okay, minus VB because it is helping. So that much less voltage is required. So V in less than minus VD on minus VB. V in greater than minus VD on minus VB. All right. So here it is V in less than minus VD on minus VB. Diode D1 is on. So KVL around the loops gives us plus V in plus VD on minus VB minus V out is equal to 0. So V out will be V in plus VD on minus VB. Okay, so it tracks the input, output tracks the input, but with a shift of VD on minus VB, and we have done this before. This will be 0.7 minus 2 volt. That will be minus 1.3. Level is 1 minus 1.3 level. Okay, and when a V in is greater than this, diode D1 is off. My output is 0. This we have seen before. This type of clipper circuit is called as a bias positive series clipper. This is clipper number 13 actually. So let's plot the VTC curve. So VTC curve will be VD on minus VB. Okay. So here it is. This is VD on minus VB below. Minus means below. Okay. So if I substitute it over here, the y-intercept will become minus 0.7 over here. This. So that's why we have a line. This line is called as V in equal to VD on minus VB. Okay. VM. This is V in line. This is VD on minus V in plus VD on minus V in line. You can say V in plus VD on minus VB line. I think here it was V in earlier case. Yeah. V in plus VD on plus VB. Here it is V in plus VD on minus VB line. Okay. So this will be the level clipping level. Why it is positive? Because we consider VB to be greater. So this is around minus 0.7 plus 2 to this will be 1.3. That's why positive. So beyond this, if V in is greater than this, diode D1 is off. And when diode D1 is off, the output is 0. And below this, diode D1 is on. So it will follow this line V in plus VD on minus VB line. I hope it is clear. Now let's come to this now. So over here we have drawn, first of all, we'll draw input output waveform. Input line you draw. Then you consider over here V in equal to 0. So V in equal to 0, what does this mean? VD on minus VB. So the line will be 0.7 minus 2. So somewhere around 1 minus 1.3 it will come. So here, let's say this is minus 1.3. Then you draw this line exactly, symmetric to V in, but below it. So this difference is 1.3 volt. Okay. And then this is my clipping level now. So what will happen now? What will happen now? This is, let's say, 1.3 volt. Minus, I mean, this level is 1.3 down. Okay. Now, what is the level? V in should be minus of, this is how much? 0.7 minus 2. Okay, so let's say minus 1.3. So plus 1.3 volt. V in greater than 1.3 volt. So this level is positive. Okay, so V in with reference to this is my reference, right? So if V in is greater than, V in is, this is diode is on and this is diode is off. So V in is greater than 1.3 volt, where when it is possible V in, now this is V in, this is what? V in plus VD on minus VB line. Yes or no? So V in is greater than 1.3 volt, where it is in this case over here. Okay, this is the level now, plus 1.3. So you go above one. This is 1.3. This is 0 now. Consider it 0, and you are going above by 1.3. So above this, your output is 0. Okay, this is my new level. Now below this 1.3, my output will follow the input, but with the shift of VD on minus VB. So that is how we have drawn this line. Are you understanding? Yeah. Let me show you its clipper number 13 input output waveform. Okay. Clipper number 13. Let's consider. Yeah, this one. This is the same thing. This I write it as 2 volt. Let's see what happens. This is my input waveform and this is my output waveform. See, if I show you both together, see, this is how it will look like. Correct? Exactly in the same manner, right? See this. Okay. Understanding? This is 0 level. This is 0 level, as you can see. So it's exactly the same analysis and the waveforms. So these are all the 13 clipper circuits which we have in your syllabus. Nothing extraordinary out of this will come in exam. You will have a clipper circuits out of these 13 clippers only. Now let's say we have 10 minutes more, we'll wind up the clamper circuits also. Okay. So let's consider the clamper circuit quickly. Will not put much time in this. So clamper is a network constructed of a diode, a resistor and a capacitor that shift a waveform to a different DC level without changing the appearance of the applied signal. So it would either clip the waveform above the DC level, below the DC level. So we have a positive shunt clamper or a negative shunt clamper. That's it. The DC level of the entire waveform is getting shifted. The output waveform is not at all distorted at all. It's all about the DC level shifting up and down. Okay. So this is my clamper number 1. We have a diode which is in parallel with the output and a resistor also, and we have a capacitor also. You know the RC time constant, the resistor and the capacitor value should be greater than the time constant of the circuit, the time period of the circuit. So let's consider the constant voltage model for the diode. And we have a square waveform. Input and input is +5 to -5 square wave. So VM is +5 volt. All right, and time period is 1 millisecond. So this RC time constant, R into C, should be greater than this 1 millisecond. Okay. So I've already explained that in the class why it should be, so that the capacitor does not discharge and act as a battery. So let's say during positive half cycle, what happens? This is my circuit. Let me draw it again. We'll go it quickly because this we have done it before. So my circuit is this. V in, this will be capacitor. Then we have a diode like this. And then we have a resistor. Correct? Plus minus V out. So when does the diode turn on? Diode turns on when V in is greater than VD on. Same concept will be there, right? Okay. But here second thing is happening, the capacitor also gets charged. So circuits gets reduced to this network. Over here, my output voltage is parallel to VD on, so around 0.7. At the same time, the capacitor is charging with this polarity. The capacitor charges instantaneously to VM. It should charge up to VM. and the voltage across the capacitor gets built up. The voltage across the capacitor is VC1 and reaches up to Vm, okay, with a polarity plus minus VC1. So now we apply the KVL around this loop. So what do we get? V in plus V in minus VC1 minus VD on is equal to 0. So how much is VC1? V in minus VD on. And V in is nothing but Vm. Vm is 5. So VC1 will be 5 minus 0.7. This will be 4.3 volt. So the capacitor voltage across the capacitors C1 during the positive half cycle reaches up to 4.3 volt. All right. Now let's go to the negative half cycle. During the negative half cycle, diode is off for V in less than 0 volt, correct? So diode is off for the entire negative half cycle. Now, when the diode is off, the capacitor can discharge via R1, but the discharging period is so slow that the capacitor will hold the charge. This is the discharge part. So earlier it was holding the charge in this direction. Yes or no? So we'll apply the KVL in this loop now. We'll go V in minus VC1 minus V out is equal to 0. So what will be output? V in minus VC1. So it will hold the charge, right? Capacitor will hold that charge and will not discharge. It will remain it as 4.3 volt only because of the discharging time period is very, very long. So output voltage will be minus Vm minus VC1. Minus Vm is minus 5 minus 4.3 minus 9.3 volt. So output during the negative half cycle is minus 9.3. So over here, this is my input output waveform. My input waveform is red in color. My output waveform is green. So for the positive half cycle, the output remains at 0.7. For the negative half cycle, it remains at 9.3. So if you add these two quantities, it has just been shifted down. If you add this, this is 10 volt only. 10 volt peak to peak. It's just that it's shifted down. And how much is the shifting level? See, it is shifted down by, earlier it was 5, now it has become 4.7. So it is shifted down by 4.3. So here minus 4.3 is my DC level, new DC level for this green color waveform. Are you understanding? The entire waveform got shifted down. That's it. So this type of clamper circuit is called as negative shunt clamper because the waveform is shifting down. Okay, this was clamper number 1. Easy. Let's finish off the other circuits also within 5 minutes. Clamper circuit number 2. Let's say that we have to design a clamper, diode clamper, to generate the waveform such that it goes up. So from plus 5 it goes to 9.3. So how much is the shift above? It is shifting above by how much? From 5 to 9.3. So how much is the shift? From 5-fold to, sorry, 4.3, no? Yes. So my DC level of my output should be 4.3. And from minus 5 it is going to minus 0.7. So again, 4.3 volts shifting above. See, the waveform is not getting distorted. The waveform is shifting up. That's it. The total peak to peak will be in 10 volt only. So here, see, here after the inspection, we say that it's a job of a positive shunt clamper because it's shifting up. By what level? It's shifting up by 4.3 volt. So from the output waveform, it is clear that constant voltage model can be employed with VD on equal to 0.7. And from the output waveform, during negative half cycle, the V out is minus 0.7. See, V out is be minus 0.7, right? And during the positive half cycle, output is 9.3. So the diode clamper circuit which does this job, which will do this job will be this. This is the diode clamper circuit. Just connect the diode in reverse and you will get the shift at the positive side as 9.3, negative side as minus 0.7. Let's see how this works. First of all, select R and C values very high. I mean, C1 is 100 microfarad and R1 is around 10 kilo ohms. So the discharging time of the capacitor will be very, very long. So let's start. Now always, it's a clue. When the diode is reverse, when a diode is connected reverse like this, always start with negative half cycle. Because for the entire positive half cycle, the diode will remain off, correct? It is only during the negative half cycle that it will turn on. Now let's start. So during the negative half cycle, that's what I said. The diode is turning on when input is less than minus VD on. You again agree on that? when input is less than minus VD on. Yes or no? You have seen that before. So the circuit reduces to this and output is equal to minus VD on or minus 0.7. So during the positive half cycle, our output is equal to minus VD on or minus 0.7, which is correct. This is what we want. So negative half cycle, the picture is clear. Now let's go to positive half cycle, how this becomes 9.3. So at the same time, because this is holding, I mean, output is holding minus, 0.7. At the same time, capacitor charges towards minus Vm, reverse. It charges reverse. Okay. So the capacitor instantaneously charges towards minus Vm, and the voltage across the capacitor Vc1 builds up and reaches up to minus Vm. Now, if you apply the KVL around the loop, you will get plus Vin plus Vc1. The polarity is minus plus. Huh? Just remember the polarity as this plot, not plus minus, it's minus plus because it's storing minus negative charges. So V in plus V C1 plus VD on, because you're going from negative to positive. So rise in potential. So plus VD on equal to 0. So VC1 will be minus V in minus VD on. And in the negative half cycle, V in is minus VM, which is minus of minus VM, which is plus VM. I mean plus phi. So over here, VC1 will be phi minus 0.7, which will be 4.3. So the capacitor, voltage across the capacitor during the negative half cycle is 4.3 in this direction. Just remember this. Now we go to positive half cycle. So we know during the positive half cycle, the diode will remain off during the entire positive half cycle. So for V greater than 0, my diode will remain off. But my diode will remain off. The diode, I mean, the capacitor can discharge via the resistor, but the discharging time constant is very, very, high compared to the time period. So it will almost not discharge, it will hold that charge. So how it is holding the charge? Like this, plus here on the right hand side and minus negative over here. So when we apply the KVL around this loop, we'll get plus V in plus VC1 minus V out is equal to 0. So what will be V out? V in plus VC1. And how much is V in? VM. So VM plus VC1, which is 4.3 volt from the earlier case. So hence the output will be 9.3. And this is what we want. Okay. So this is what we wanted, that the output reaches to 9.3 during the positive half cycle and reached up to minus 0.7 during the negative half cycle. So the amount of DC shift will be 4.3 volt. Are you understanding how does the clamper circuit works, everyone? Yes or no? Come on, reply. Two more to go. Yes, it is a positive shunt clamper because it is shifting the output waveform above, not below. So now there will be two variations, either connecting the battery over here in reverse or in the opposite direction. Let's quickly see now. Clamper circuit number 3. One more to go, last part, just a few minutes more. Okay, here my diode is there and a battery is connected over there. VB is 2.7 volt, let's say. So can you tell me when does the diode turn on? We'll start with positive half cycle or negative half cycle. Diode is connected this manner. So diode will ever have a chance of turning on during positive half cycle? No, it will turn off. So we'll always start when the diode turns on. So diode turns on during the negative half cycle. When does the diode turn on? Can you tell me? We have done so many circuits now. So V in has to be less than minus VD1 will come, whether plus VB or minus VB. Plus minus. Come on, tell me fast. Hello. Plus VB, na?
Yes.
Or it will be minus VB. Plus VB, but if you take the
Plus.
bracket over here, bracket like this, if you open the bracket, then it will be minus VB. Are you understanding? It is adding
Yes.
up to this, na? It has to overcome this voltage plus the diode voltage. So it is V in less than minus VD1 plus VB. So this will be 0.7, this will be 2.7. So how much this level will be? 3.4, right? Correct. So we have a sinus triangular signal, triangular waveform as the input, where VM is plus 10 and minus 10 over here. VB is 2.7. So we have to write this assumption always. So during the negative half cycle, when Vin is less than 0, diode will turn on when Vin is less than minus VD on plus VP. Minus VD on, minus VD on plus VP. So it's not 3.4. It's minus VD on plus VP. So how much it should be? It's actually helping the diode, right? It's not opposing the diode. So it will be plus VP. Okay. So that much amount of voltage will be reduced. So how much it will be? This will be 2.7 and this will be minus 0.7. So it will be 2 volt, right? Yeah, it will be 2 volt. So here it is. Vin is less than minus VD1 plus VB. The output will be equal to minus VD1 plus VP. So that will be output will be equal to 2 volt now. Did you get it how it is 2 volt? See earlier here this VB voltage is helping the diode to turn on. So for the helping case it will be plus VB. Okay, not inside the bracket. It will be outside only. So now the diode will be on when the input is less than 2 volt. Okay, so input is less than 2 volt, output will be at 2 volt only. So during the negative half cycle, the V out will be at 2 volt only. So at the same time, capacitor charges instantaneously in a negative direction. So plus minus like this. Now let's apply the KVL in this loop. You will get V in plus VC1 plus VD on minus VB is equal to 0. Why minus VB? Because it is plus minus, fall in potential. So VC1 will be minus V in minus VD1 plus VP. Now during negative half cycle, V in is minus VM. So minus of minus VM minus VD1 plus VP. So it will be 10. VM is 10 minus 0.7 plus 2. So it will be 12 volt. The voltage across the capacitor will be holding its 12 volt right now during the negative half cycle. Okay. And now we go to positive half cycle. We know during the entire positive half cycle, the diode will remain off. Okay. But the capacitor can discharge via the resistor, but it will not discharge because the discharging time period is very, very slow. So we'll apply the KVL in this loop over here. So KVL around loop 2 will be V in plus VC1 minus V out is equal to 0. All right. So here V out will be equal to V in plus VC1. Now during the positive half cycle, V in is equal to VM. So VM is around 10 volt and VC1 is around 12 volt. So the output voltage will be 22 volt during the positive half cycle. All right. Let's see how it looks like. Here it is. See, this is the input waveform. The level will be around 12 volt. So during the positive half cycle, it is shifted above, right? As you can see, shifted above. By how much? So 10 becomes 22. So it's shifted above by 12 volt level. So in the positive, negative half cycle, it is reaching to 2 volt. In the positive half cycle, reaching to 22 volt. So this is my clamper number 3. Understood? Any doubt, anyone? So this is called as a biased. Why? Because you have connected a battery. And since it is shifting the waveform above, it is called as a biased positive shunt clamper. All right. Let's come to the last circuit. So clamper number 4, we have to design a diode clamper to generate the steady state waveform output from the input. So here it is shifting down, but the level is slightly different. It's not 0.7. Okay, so we have to connect a battery, just remember. So it's shifting from positive to plus. This shifting from, let's say, so how much is the level, clamping level? It's going from 10 volt to 6 volt, correct? In the positive half cycle, and minus 10 to minus 14. So how much is the level it is shifting? Down by 4 volt. Yes or no? So somehow we have to connect a battery. Let's say we consider 0.7 as the voltage across the diode. So somehow we have to add a battery of 3.3 volt externally. Let's see. This is the clue we get from here, right? Yeah, here it is. Minus 14 during the negative half cycle and plus 6 during the positive half cycle. So this clamper circuit will do the job. Plus the diode connected this manner and VB voltage connected like this. Because it has to overcome 0.7 plus this voltage VB. So let's find out how much is this voltage VB is. So we want plus 6 during the positive half cycle, right? So the diode should be on whenever Vin is greater than VD on plus VB. So how much should be VD on? VB, how much should be VB? So this is 0.7. So this should be 5.3. I think 5.3 was correct. Yeah, 5.3. We want 6 volt, right? So for 6 volt, it should be 6 volt, it should be 0.7 plus 5.3. Yeah. Understood how 5.3 it should be? Because we want, so when the diode is on, greater than V should be greater than VD on plus VB. This is 0.7. And the circuit will reduce to this and output will be VD1 plus VB. So this is zero point 0.7. This will should be 5.3 for the output to be 6 volt. Correct? Yeah. Now at the same time, the capacitor will charge in this direction and we'll apply the KVL around the loop. Let's find out how much does the capacitor store energy. So V in minus VC1 minus VD on minus VB equal to 0. So VC1 will be V in minus VD on minus VB. V in is VM in the positive half cycle. VD on is around 0.7, VM is 10, and VB is 5.3. So VC1 will be 4 volt. VC1 is my clipping level actually, I mean clamping level. So not the clipping level. So the VC1 is the voltage across the capacitor during positive half cycle. So it is charged up to 4 volt. Let's see what happens during the negative half cycle. During the entire negative half cycle, the diode remains off. Okay, so it will be replaced with open circuit. So what happens to the capacitor? Capacitor discharges, but the discharging period is very, very large. So the discharging is very, very slow. So it will hold the entire 4 volt charge. So, okay, the capacitor will hold that charge of 4 volt and act as a battery. Now we apply the KVL around the loop. So it will be plus V in minus VC1 minus V out equal to 0. So output will be V in minus VC1. During the negative half cycle, V in is minus VM. So V out will be minus VM minus VC1, which is minus 10, minus 4, which is minus 14. So output will be minus 14. This is what we want, right? This is what we wanted initially, right? From minus 10 to minus 14. So here is my input output waveform. So the red color one is my output and the green color is my input. All right. Oh, sorry, the other way around. The green one is my input. Yeah, the red one is my input and the green one is my output. Okay, so the waveform is shifted down here. The positive half cycle it is plus 6 and the negative half cycle it is minus 14. So this is inconsistent with the circuit which we have done. So this is called as a biased negative shunt clamper. So if you want the level to go down, you have to connect the diode like this. If you want the level to go up, you have to connect the diode in reverse. And then we have to add the battery accordingly. So this is how you design a clamper circuit. Okay, there is no input output VTC curve for this clamper circuits. We have only input output characteristics. Clamper circuit are easier to explain comparatively to the clipper circuits. All right. So this is how we can do the analysis for the entire clamper circuits. Let me check if I have some simulation file for my clamper circuit and then we'll wind up for today. Clamper number 4. Yeah, sinusoidal waveform, it will do. No problem. Okay, here it is. It's entire shifting down. So that is how here the battery is connected opposite. So that is fine. Let me see if I have a battery connected. Yeah, this is the one. So ignoring the first cycle, this is how the waveform will look like. Now this is a sinusoidal signal. We can also generate a triangular signal from it. So the entire waveform is shifted down. Entire waveform is shifting down. The black one is the input, the blue one is my output. And here also we are getting the similar nature. So this is all about clamper and clipper circuits. Okay, everyone, thank you.